Hello, everyone. Welcome back to our public science lecture series. Today we have Dr. Ryan Anderson from the U.S. Astrogeology Science Center. Um, Dr. Anderson received his PhD from Cornell University, and he went on to do he was a shoemaker postdoctoral fellow at the um, U.S. Geological Survey Astrogeology Science Center, so mixing Earth and space science, and that's where he's continued to work on today. And so we're going to learn more about the Mars mission, the most recent Mars mission, Perseverance. And Dr. Anderson, please take it away.
All right. Well, thanks for having me. What side I didn't mention is that we go way back to undergrad. We're both astronomy students at University of Michigan. So it's great to be here and catch up, even if it's just virtually. So today I am excited to be able to share some of the first results from the new Mars rover mission, Perseverance rover. And so this first slide is just a preview of what's to come. This is the mass cam mosaic from where we landed in Jezero Crater. And so I'll just briefly introduce you to the rover, what it does, what its mission is, and then I'll just show you some of the really cool stuff we've been getting down in the last month or so, and talk about where the mission is going to go from there. So just to step way back to the sort of big picture, why are we going to Mars? Mars is really interesting because it's this somewhat Earth-like planet, but today it's really cold, it's really dry. But in the past, there's hints that there was water. It may have looked like the picture on the right, or maybe it looked more like this. We don't know how warm it was. We know there was water, but maybe it was just there occasionally and was mostly frozen. So there's this big question about like how warm and wet was it, and why did it change from that pretty wet climate to the very, very dry climate that we have today. And we can do a lot with satellites and rovers, but one of the big things that this mission is doing is it's paving the way for sample return. So the objectives of the Perseverance rover are, first of all, to study the geology of the landing site. It's a really interesting landing site that I'll tell you a little bit about. This is also a specifically astrobiology focused mission. We're looking for evidence of life, not just water, not just a habitable environment, but is there evidence of actual biology happening? But then the big thing is we're going to be collecting samples. We're going to be drilling into the rocks and taking little core samples, scooping up soil, and storing those in the rover. And then we will deposit those on the surface for a future mission to retrieve. And so this is the beginning of a multi-stage series of missions to bring samples back from Mars so that we can analyze them with all the latest and greatest technology in Earth labs for decades to come. And then sort of the bonus objective of the mission is to prepare for humans. So we'll be studying the environment, and we have some instruments on board that generate oxygen from the Martian atmosphere as a demonstration of that technology. So that's sort of the additional objective on top of all the sort of science inherent to what we're doing. So this is what the rover looks like. This is a computer rendition, but it's a very realistic one. And you can see it has a variety of instruments. It has the mass cam cameras. These are zoomable color cameras. They're the ones that took the beautiful picture on my title slide. RIMFAX is a really interesting, exciting instrument that actually does ground penetrating radar. So it gives us a three-dimensional view of the ground underneath the rover, so we can see the layers of the rocks and how those change. Really helps us understand the geology. MOXIE is the one I mentioned that produces oxygen from the Martian air. Pixel is an X-ray spectrometer that can make a little map of the chemical composition of rocks that the rover is touching. And Sherlock does something similar, but with an ultraviolet Raman spectrometer, which is really, really sensitive to things like organic molecules, but can also identify things like different minerals. And Sherlock includes a camera called Watson. It's a copy of the MALI camera that's on the Mars Science Laboratory rover. It's a color microscopic camera. There's META, the weather station, measures the air temperature, wind speed. And the Supercam is the instrument that I'm most involved with. It's a laser instrument. It zaps rocks and tells you what they're made of, as well as having a high resolution color camera. So it's a really great payload, and it allows us to characterize the rocks and the soils that we encounter, and then we have all of that sort of context information for when we take a sample and store it inside the rover. And so speaking of sampling, this is what the sample tubes look like over here on the left. They're pretty small. You can see the 1 centimeter scale bar, but the rover will have the ability to drill into the rock and take these samples, and we'll actually be able to store those in the rover, collect a whole bunch of them from a variety of different types of geology, volcanic rocks, sedimentary rocks. We have a whole list of things that we want to collect with the rover. And then after we have collected them from different locations, as is shown in this sort of animation, we'll dump them on the surface in one location. And the plan actually is to, at the beginning of the mission, collect duplicate samples. And partway through the mission, we'll drop a sort of starting cache of samples, so that if then the rover breaks, we have sort of a good cache to begin with, but we'll keep some of the samples, some of those duplicates, and we'll continue outside of Jezreel Crater and collect even more. And hopefully the rover will survive, and we'll have an even bigger cache later on that we can drop before the sample return mission arrives. But either way, we'll get some really, really interesting samples that can be returned to Earth and tell us a lot about the history of Mars. So that's a sort of brief introduction to the rover itself. Now I'm going to introduce you to the landing site. So this is Mars. This is a nice view of Mars produced by the Astrogeology Science Center where I work. Just a note, the color is a little bit exaggerated. Real Mars would look a little bit sort of more muted than what you see here. This has been stretched to bring out the contrast a little bit. But this picture does include Jezreel Crater right on the edge. So we're going to zoom in up here. And then I'll label a few of the key features here. So Syrtis Major is this big black area. This is a volcanic lava plain. There's a volcano down here, and a lot of this is basaltic rock, so it's dark colored. And it's pretty clean. It's not very dusty here, so we can actually see the black rock rather than the red dust. This big crater Antoniadi, and then Isidis is this giant impact basin from very, very early on in Martian history. And ringing Isidis, there's these fractures in the crust called the Nili Fossae. And Jezero is this crater right here, right on the edge of Isidis. So it's at an interesting location where it's at the intersection of the Syrtis Major, the Isidis Basin, and then the really ancient bedrock around the Nili Fossae region. So this is what the Jezero crater looks like from orbit. This is a color composite from a variety of different satellites. And you can see in this picture why Jezero is interesting. If you look over here on the west, you see a meandering valley that cuts through the crater rim. And then over on the east, there's a meandering valley that comes out of the crater and continues. So to have that happen, you actually have to fill up the crater and overflow. That's the only way you get an inlet and an outlet channel. And so that's really, really good evidence that Jezero Crater was a lake. The other evidence, if we zoom in, is this. This is thought to be a delta. So a delta forms when you have water flowing and carrying sediment, and that water encounters standing water. So suddenly the water from the river slows down when it reaches the standing water, and it can no longer hold that sediment. The sediment falls out and it forms a deposit right at the mouth of the river where it enters the standing water. And it forms this sort of fan shape. It's familiar if you've ever looked at a satellite photo of like Mississippi, the Mississippi River Delta is sort of this bird foot shaped deposit dumping all the sediment from the Mississippi River into the Gulf of Mexico. Similar thing happening here, obviously much smaller, but it's the same sort of process. And we're really excited about a delta because when you have all that silt and sand settling out, it's really good at capturing and preserving any organic molecules that are in the water. Any microbes that are in the water get trapped in that really, really fine-grained sediment, and then it gets preserved. And so if you want to look for life on Mars, you go to a place where you know there's water and you know there was the environment where it would be best preserved, and that's a delta. So that's why we're going to Jezero Crater. This oval on this picture is what's called the landing ellipse. That was the area of uncertainty for the landing. You know, landing on Mars is not a pinpoint thing. Usually there's some uncertainty. And so we didn't know where in this circle we would land. You know, it's more likely to land in the middle than at the edges, but we weren't sure exactly where we were going to land until we actually did it. So here's a perspective view. This is some data that was produced, stitched together by the folks at Astrogeology where I work. And this is the most precisely registered map of Mars ever made. And the reason we made this is because we were working with the engineers at JPL who built the rover. And the rover has what's called terrain relative navigation. It has the ability, as it's landing, to take pictures of the surface and steer to a safe place. That's the only reason we were able to land at a landing site like this that has all these cliffs, craters, and sand dunes in it. Previous missions wouldn't have been allowed to land here because it was not safe enough. But with this new technology, the rover can steer to a spot that's safe among the hazards. And I'll show you that in a little bit when we look at the actual data from landing. But to do that, you have to have a really good map of your landing site so you know exactly where those hazards are. You don't want to map a hazard and it turns out it's actually 20 meters to the east, and then you land on it and you die. So USGS produced this really high resolution mosaic and topography that were used to help the rover steer to a safe location. And this is a close-up on the delta, just to highlight why the scientists, myself included, are excited about this landing site. See these curved light tone layers that sort of truncate each other. That's sort of the telltale sign that you had a river channel that was meandering back and forth. So the river, as it moves to the side, it deposits these curving layers, beds of sediment, and then the river meanders the other way, and it carves into those and deposits new sediment that truncate those other layers. And it builds and builds and builds. And so when you look at the delta, you see a whole story of the river moving back and forth and back and forth. And this is sort of the smoking gun that this is a delta, that you had this meandering river channel. So if you drive the rover across here and study these in detail, you can actually put together a really complicated story of how the water behaved, how long it lasted, and what the flow was like. You can learn a lot about the lake and the river system on Mars. And so we're really excited to get to this location on the Delta, but there's lots of other stuff along the way as well. But I wanted to highlight this because this is sort of our best evidence that this is actually a delta and not something else like an alluvial fan, which is something that can form in a dry crater with no standing water. So with that introduction to the landing site and the rover, now I'm going to start showing you videos and pictures from the actual landing. So first, I'm just going to start with this video from landing day. This starts with footage from the control room at JPL. And then the amazing thing about this mission is that the rover and the spacecraft had cameras recording high definition video as it landed. And so this video is going to cut away and show those as the events of actual landing occur. And it's honestly one of the most incredible things I've ever seen and probably ever will see. So I'll share this with you and then we'll talk a little bit about it, but I'll let it speak for itself first.
We are starting the straighten up and fly right maneuver, where the spacecraft will jettison the entry balance masses in preparation for parachute deploy and to roll over to give the radar a better look at the ground.
Indicate chute deploy.
The navigation has confirmed that the parachute has deployed, and we are seeing significant deceleration in the velocity. Our current velocity is 440 meters per second at an altitude of about 12 kilometers from the surface of Mars.
Heat shield set.
Perseverance is now slowed to subsonic speeds, and the heat shield has been separated. This allows both the radar and the cameras to get their first look at the surface. Current velocity is 145 meters per second at an altitude of about 9.5 kilometers above the surface.
Nav filter converge. Velocity solution 3.3 meters per second. Altitude 7.4 kilometers.
Now has radar lock on the ground. Current velocity is about 100 meters per second, 6.6 kilometers above the surface of Mars. Perseverance is continuing to descend on the parachute. We are coming up on the initialization of terrain relative navigation and subsequently the priming of the landing engines. Our current velocity is about 90 meters per second at an altitude of 4.2 kilometers.
LVS valid.
We have confirmation that the lander vision system has produced a valid solution and part of terrain relative navigation.
Priming. TBA is nominal.
We have priming of the landing engines.
Back shell set.
Current velocity is 83 meters per second at about 2.6 kilometers from the surface of Mars. We have confirmation that the back shell has separated. We are currently performing the divert maneuver. Current velocity is about 75 meters per second at an altitude of about a kilometer off the surface of Mars.
TRN Safety Bravo.
We have completed our terrain relative navigation. Current speed is about 30 meters per second, altitude of about 300 meters off the surface of Mars. We have started our constant velocity accordion, which means we are conducting the sky crane, about to conduct the sky crane maneuver. Sky crane maneuver has started, about 20 meters off the surface.
We're getting signals from MRO.
Tango Delta.
Touchdown confirmed. Perseverance safely on the surface of Mars, ready to begin seeking the signs of past life.
Okay, so that's pretty cool. I apologize for this bar at the top. I don't know how to get it to go away, but I think you could see the video well enough.
Weird.
So it's an amazing video. Even watching it all this time after the landing, it's just incredible. The interesting thing is, you know, that video gives the impression that we had all those pictures as we were coming down. What really happened is we just had the audio and a simulation of what was happening. We didn't have those videos until several days later. And so we heard all those things happening, but no pictures until several days later. But as those pictures started to come down among the team, it was, you know, people were losing their minds seeing these pictures, seeing the sky crane flying away like a flying saucer. It's just incredible. Those first few days when you don't have a lot of data, you're just starting to see things, but you know, every day you get something new, some new piece of one of those videos, and it's super exciting. I wanted to mention this. This is one of the still frames of the parachute. You may have noticed this weird pattern on the parachute. It's actually a binary code that the JPL engineers put on the parachute that if you decode it, which people on the internet did within minutes of getting the pictures, it says "Dare mighty things," which is a quote that JPL uses a lot. It's part of this Teddy Roosevelt quote. Far better it is to dare mighty things, to win glorious triumphs, even though checkered by failure, than to take rank with those poor spirits who neither enjoy much nor suffer much, because they live in the gray twilight that knows neither victory nor defeat. So JPL has this habit of being sort of pat themselves on the back, and rightly so. They keep landing things on Mars, so I guess they're allowed to do that. And it also has the coordinates, the GPS coordinates of the Mars building at JPL. So that's a fun little Easter egg hidden in the rover itself that people figured out. As we were landing, you may have heard them in the audio mention that we were getting signals from MRO. MRO is the satellite that orbits, one of the satellites that orbits Mars and transmits data back. But not only was it transmitting the rover data, it also took a picture of the rover while it was on the parachute. So this is pointing at an angle, and the camera that they use, the high-rise camera, is a push broom camera. So it's not like a point and shoot where it takes the whole frame at once. They actually have to scan across the scene to take the picture. So they did this amazing coordination where the spacecraft sort of rolled as it was taking the picture to capture the Mars 2020 on the parachute. So there's the parachute, there's the spacecraft itself as it was coming down into the crater. Just a spectacular picture. It's just amazing. Everything about this landing is just amazing feats of engineering and science. This is the picture, a series of pictures from the lander vision system. This is a fisheye lens, and this is the camera that was actually used to match up what the rover was seeing with that map that astrogeology made. And if you pay attention in the lower right, I'll let this loop again. This, the little picture in the lower right follows the heat shield as it falls down. You can actually watch it impact the surface and kick up a giant spray of dirt as it hits. Not the primary purpose of this camera, but kind of a cool thing that people were able to do following. You can see, boom, kicks up this big sort of divot of dirt out of the landing site. But this camera is the one that was used to pick the safe spot as it was coming down and divert the rover to avoid all the rocks and cliffs and things and land in a nice, safe location. Again, these pictures went public and people immediately started playing with them. That's one of the nice things about Mars exploration. There's all these people who are excited and play with the pictures once they come down. So this is by Kevin M. Gill. He took one of those pictures from the LBS, the fisheye, and straightened it out and added realistic coloration to see what it would look like, you know, if you were in an airplane flying at that same elevation looking out over the landing site. So there's the heat shield and there's all the landmarks of the crater and, you know, the dusty horizon in the distance. So the cool thing about landing with the terrain relative navigation and using that camera to map where we're going is that immediately upon landing, we got a pinpoint location of where we were in the crater. So this is where we ended up, this star, and it has been given the name the Octavia E. Butler landing site. Octavia Butler is a very famous science fiction author. And so continuing the tradition from Curiosity, which named the landing site after Ray Bradbury, a science fiction author, we chose the Octavia E. Butler landing site for our landing location. And you can see we landed here on sort of the far side of this sort of lobe of rougher terrain. And so that's really interesting geologically. It also is an obstacle for us getting to the delta. So we'll talk a little bit about that later. But it's a really nice landing site. And to show you how good that terrain relative navigation worked, here is a map of the hazards. So red are places where you don't want to be. Not all of this red would actually kill the rover, but it would not be a great place to land. So you can see as we were coming down, the TRN system said, there's a patch of blue right there. We're going to steer and land right there, not on these rocks over here, not on these sand dunes over here, not in this crater, right there in that one safe patch. And so it worked like a charm. Everyone involved is really relieved and really proud that the system worked as intended. And it's a great demonstration of the technology and how we improve every time we land on Mars. So here's a little bit of a closer view of our landing site. You can see these two white patches are actually places where the rockets on that sky crane actually blew away the dust and sand and cleared off some of the light tones or bright rock underneath. You can see other locations. There's the parachute and back shell. There's the descent stage where it crashed, so that the sky crane, after it drops off the rover, it flies away, uses all its fuel to get as far away as possible, and it creates a giant impact in the surface. And then here's the heat shield that we saw in that other animation. That's where it hit the surface. But like I was saying, we didn't get all that information at first. At first, we just got the sort of the narration from that video, and then we got this picture. And this was the first picture we got from the rover. And it's an incredible feeling to be watching and waiting and, you know, knowing the thousands of people and years and years and years of work that go into one of these missions. And then it all hinges on this sequence that nobody can control. The rover's doing all of that by itself. And then you get this picture back, and suddenly the place that you've been studying from orbit, it becomes real. And you see the rocks on the ground, you see your wheels on the soil. It's just an amazing feeling. I was lucky enough to be involved in the Curiosity rover when we landed there, and it was just as incredible then. You know, you've been looking at this place from orbit for so long, and then suddenly you're there. And so even though this is not the prettiest picture, it's a really powerful picture, especially for those of us who've been working on the team. And then we started to get other pictures down from the hazard cameras and the nav cams. And so this is one of the first pictures. And you know, it's not much, but those first couple of days, this is like all the science team had to work with. And so I can't tell you how many people spent how many hours looking at these rocks and puzzling over, you know, why does that rock have holes in it? Why do they look bright instead of dark? You know, every possible question you could ask about these limited number of pictures. We were poring over the pictures. This is a screen grab from one of our first press conferences. And this is literally what our science looks like at the beginning. Is like, yeah, those ones have holes and those ones are light and then those ones are dark. Why? What are we looking at here? And that's where we start. And from there, you know, we build more sophisticated hypotheses and we fit what we're seeing in with what we know from orbit. But it really starts with these really basic observations. Another thing I'll point out that's not labeled in this image, there's this bright patch here. That's where the rockets of the landing stage cleared away the dust and blasted away the dust and sand and exposed these rocks. And I think it's really cool the way that the Sky Crane landing works. Is just suddenly there's a rover there after billions of years of just wind and erosion. Suddenly this alien spaceship comes down from the sky, blasts away the sand, and there's a rover on the ground. And so these exhaust plumes are kind of cool, and they sort of dig up the rocks around us and give us a glimpse at rocks that have been buried for possibly billions of years. Another cool thing, and I wish this bar at the top would go away. I don't know how to make it go away, but in this picture from the hazard cameras, it's stretched really, really hard, but in the distance, we actually caught a plume of dust kicked up from when that Sky Crane stage flew away and crashed into the surface. There was some debate about whether this is a plume of dust or whether it's like an action movie fireball. I'm pretty sure it's dust. The fuel on that rocket burns clear, as you saw in the video. There's no flames shooting out. So I think this is a plume of dust from where it impacted. But in any case, it's related to the impact of that stage as it crashed into the surface. So that was another cool thing that came down a couple days after that. So then we started getting the science data, and it got really exciting. So this is the full-sized mass cam panorama. I showed part of this as my title slide. This is the color science camera on the rover. It's the successor to the one that was on the Curiosity rover, but the ones on Perseverance can actually zoom in and out, which is really nice. It helps with the stereo 3D reconstruction of the site. But you can see here the bright patches from the rockets clearing away the dust. You can see in the distance, I'm going to click and we're going to show the full resolution of this. So these hills here, these cliffs, those are the edge of that delta. And these big hills in the background, that's the crater rim. And this low part is where the valley is cutting the crater rim. And this little butte over here is a remnant, a outlying piece of the delta where a lot of erosion has happened, but there's a mesa sitting there sort of separate from the rest of the delta. And then in the foreground are some sand dunes, some scattered rocks, and just a very tiny hint of that really rough area that is going to be a challenge for us to go around. But this panorama and this picture down here, this was taken with the camera zoomed out. So let me show you what it looks like when they're zoomed in. So sorry, I don't know about this thing at the top, but anyways, if this thing wasn't hiding the top view, this is the zoomed in panorama. They did a panorama all the way around 360. This is just a small part of it, but I'll zoom in on it for you. That's that butte using the full zoom capabilities of that camera. It's just spectacular. You can see the fine layers of the capping rock and then some angled layers possibly. Those are sort of the telltale sign of a delta where you have those dipping layers. And then in the foreground, this rough stuff is again that island of rough terrain that we're going to have to avoid. And then these boulders in the foreground that we're still studying and we're still making sense of among the science team. trying to figure out what these boulders are, what they're telling us about the geology of this area. So reminder, this is where we landed, this dot here. And the grid on here is, before we landed, the science team split up the landing site into all these little postage stamps. And each postage stamp, one person on the team had the assignment to map that area. And so we put all our maps together and we had a really high resolution geologic map of the whole landing site. And to keep things straight, we gave them all names. And the theme that we picked for the names were famous national parks and national monuments around the world. So the location where we landed is in the Canyon de Chelly quad of the map. And Canyon de Chelly, if you're not familiar, is a location, it's a national monument within the Navajo Nation in northern Arizona, which just coincidentally happens to be pretty nearby where I work here in Flagstaff, Arizona. The Navajo Nation is just to the northeast of us. And so this is what it looks like at Canyon de Chelly in Arizona. And it's sort of a nice tribute. You know, if you took out all the plants and the blue sky, this would look pretty Mars-like, these red rocks, these buttes, the tilted layers. And so it's, you know, the geology of this area is very Mars-like. And so to recognize sort of this link with the Navajo Nation and the geology of the area and landing in this quad, the mission has decided to actually use names in the Navajo language for the targets and the landmarks in this part of the landing site. And so this area of rugged terrain has the name Seita. I have no idea if I'm pronouncing that right. I apologize to native speakers. But that essentially translates to sand dunes. And you can see all these little ripples here among the rocks are sand dunes. And then Hahootsa is the Navajo word for crater. And so there's a big crater in the quad that has been assigned that name. And remember, we landed over here. And then on the ground, when we target things, we shoot so many rocks with the laser, with the cameras, that we have to give them names. If you give them numbers or, you know, some sort of, you know, automatically randomly generated code or something, we need to be able to talk about these things. We need to give them names that people can say and can remember. And so that's why we need this list of names. And so we actually worked with the Navajo Nation to get an approved list of names to use. And so the first targeted by Supercam on the surface, first target name assigned on the surface is given the name Maz, which is Mars in Navajo. And we're continuing to use Navajo names for our other targets as we go forward with the mission. But since I'm on Supercam, I'm going to share with you the Supercam data. So here's the remote micro imager. The telescope for Supercam can take pictures as well as collect the signal from the spectrum. So here's what the telescope shows us of this rock. It's a nice flat, bright rock. It's a nice big target for us to make sure we hit our target the first time we tried to shoot something. And then we fired the laser. And the way that this laser works is it can do a few different things. But for this first observation, we did what's called laser-induced breakdown spectroscopy, where we focus the laser light very intensely on one point, and it creates a little spark of plasma, actually vaporizes a tiny, tiny piece of the target. And that spark of plasma gives off light, and the same telescope that collected this picture collects that light and sends it into a spectrometer. And we split that light up, and we can use it to figure out what the target is made of. And so this is what that spectrum looks like. And you can see it goes well beyond the range which your eye can see. Your eye can see, start to see faint purples down here in the 380 to 400 nanometers, and then up to the reds up here. But our spectrometer goes well into the UV and up into the infrared. And all of these peaks are the emission lines of the atoms in that plasma from that rock. And so they're basically the fingerprint of that rock. They tell us which atoms are in that rock, and the height of the peak is a complicated relationship between how much of that atom is there, but also how easy is it to ionize that atom and get the light emitted from that particular chemical element. And so we can look at this, and those of us who have been staring at these sorts of spectra for many years can look at this and say, oh, that looks like a normal rock. It has the composition of a igneous rock. The challenge is Mars is an igneous planet. So we don't know yet if Ma'az and the other rocks around us are igneous, meaning like, are they lava? Are they volcanic ash? Or are they sedimentary rocks made of sand that came from igneous rocks? Because if you break up a lava rock into sand and then stick that sand together into a sandstone, it's still going to have the same composition as the original lava rock, basically. So we don't know the answer to that yet. We have a little bit of a hint, though. Over here in this inset, you can see that there's hydrogen, and the colors here correspond to the laser shots. We shot this one location several times, and the fact that hydrogen remains in all of the shots means that there's some water in the structure of the rock. It's not just in the dust on the surface. It's not just a surface coating. There's some water in the rock. So it's probably, if it is a volcanic rock, it's been altered a little bit. Or likewise, if it's a sedimentary rock, there's been some alteration. Water has been involved and changed the chemistry of the rock a little bit. Beyond that, we're still not sure. It's very early days. And so we're waiting to get all the other instruments online, all the other capabilities of Supercam online. There's different ways we can use the spectrometer. Instead of vaporizing the target, we can do what's called Raman Spectroscopy and measure the minerals rather than the atoms in the rock. And so once we get all of those pieces of data from Supercam and from the other instruments, we'll be able to better answer whether this is a sedimentary or an igneous rock. But even then, it may be difficult. You know, at Jezreel Crater with the Curiosity rover, it's still sometimes a challenge. If you look really closely at these rocks, it still can be hard to really definitively say, yes, that is volcanic, or yes, that is a sedimentary rock. But we have a really, really good tool set to just try to figure that out. Another target that we shot with Supercam, this time we just collected the passive spectrum, which means we looked at the sunlight reflecting off the rock. But this is just an example of another picture with the camera zooming in on this rock. And you can see this one is a little bit darker. It's a little bit shiny. There's some dust patches, but where it's not dusty, it's kind of shiny. And in these rocks, we're seeing evidence of water as well in the reflected spectrum as well. So we're starting to piece this together, but it's still really early days. There's a lot of calibration and things that have to go into using these instruments before we can really use them to their full extent. So stay tuned. There's a lot more to come. It's not just calibrating the instruments, it's also testing out the rover. You know, do all the parts move the way they're supposed to? And so these are just a couple animations of testing out the robotic arm. Can we move our arm? Can we turn the turret? Can we wiggle our wheels? You know, we go through all these tests. And then finally, after all these tests were passed, we did our first drive. So here you can see those blast zones and tracks that start from nowhere. And we just start driving. And since then, we've driven several times. But the rover works, it drives. And I actually have here a little audio file. It's super long. I'm not going to make you listen to 13 minutes of rover driving, but just to give you an idea, we have microphones on the rover. This is the first time we've recorded sound from Mars. And I'll just stop talking for a minute so you can hear what it sounds like to drive on Mars. So I'll spare you all 13 minutes of it, but you can hear the creaking of the metal wheels as they slowly drive over the rocks. If you listen to more of that, you hear pings and dings as you know the metal flexes and the rover, you know, this big heavy rover drives over these rocks. It's really cool. We also have, actually I forgot to show it on the previous slides. Along with our Supercam, we have a microphone on there, and you can actually hear the sound of that little spark occurring on the surface. So I'll just play that. That's much shorter little clip. So Star Wars, it's not. It sounds more like a snapping sound, or I always liken it to bubble wrap popping. That's what it sounds like in person. But it's really cool. We have this sort of new sense on Mars. We've never had microphones on Mars before. So we can use these to measure things like the speed of sound based on where the laser is hitting and how long it takes for us to get the sound signal, and the hardness of the rock, the wind speed, all sorts of cool things you can do with the microphone. And then just recently, the rover dropped this piece of called the belly pan. Plunk, it dropped down on the ground. This was there to protect that sampling system from all the rocks and pebbles that get kicked up during landing. And then just the other day, we dropped this thing. This is the shield that protected this. This is the folded up Ingenuity helicopter. And right now, the rover is in the position as we speak, where we are going to drop off the helicopter. And then for the next month or so, the rover is going to be sitting off to the side, and the helicopter is going to be testing the first attempt at flying on another planet. So here's a little video showing sort of a CGI version of what that's going to look like. The helicopter has a couple of little cameras, so it can point down, take pictures, return those to the rover. But mostly it's a technology demonstration just to show, yes, we can fly even in the thin atmosphere on Mars. It's sort of a cool technology to, once it's proven, then we can think about using it on a bigger scale for a scientific purpose. But for now, we're just helping to test that out. So this is where we are right now. That's where we landed. We've driven over here. We've dropped off. We're going to drop off this helicopter very soon. And then the rover will park somewhere and the helicopter will do its thing, fly back and forth for a while, do a bunch of tests, and then we'll continue on with our science mission. So like I said, Seita, this area here is going to be a challenge for us. We can't drive across it. So we're right now in discussions about, are we going to go counterclockwise around here, or are we going to go clockwise and then try to cross this narrow neck? And discussing, are there sites along both of these routes that we want to visit? That's still up in the air, but the eventual goal is to get to the delta and then drive up on it and then up into the crater rim. So this is a tentative path. Once you get to the delta, we would probably do something like this, seeing the sites along the way, taking samples along the way, and then probably deposit our initial cache of samples there and then drive up out of the crater and continue to collect samples up into these highlands, this really, really ancient rocks, and then potentially have an even better cache of samples a couple of years down the road once we're outside of the crater. So I'll conclude here with, this is a quote that was shared by Sanjeev Gupta. He's a member of the science team, and the day of the landing, our first science meeting post-landing, he shared this quote, and I thought it was just perfect. So it goes, "This is a great moment when you see, however distant the goal of your wandering, the thing which has been living in your imagination suddenly becomes part of the tangible world. It matters not how many ranges, rivers, or parching, dusty ways may lie between you. It is yours now, forever." And so I accompanied that with this mass cam view of the delta itself and the river valley in the crater rim. So that's where we're going. And it's many ranges, dusty ways in our distant future for the rover, but we can see it now. It's real. It's a landscape. It's not a picture from space. And so the next few years are going to be really exciting as we're able to explore this landscape, do some really, really cool science, and then hopefully collect some samples that will be returned to Earth someday. So with that, I'll leave it here. Please follow along the mission. There's lots of really cool stuff to go. We're on social media, and it's a really exciting time for Mars exploration, and it's going to be really fun as we get this rover up and running, get everything calibrated and ready to go, test our helicopter, and then we really start driving. We really start the rover mission in another month or two, and so it should be fun. And so I'll leave it there, and we've got a little bit of time for questions.
Thank you very much. That was really, really fun. And yeah, every single time I see the landing videos, it's still like, oh my gosh, this is so amazing. So
I'm telling you, it was so hard not to just like shout it from the rooftops how cool those videos were. We had to keep our mouths shut until they went public.
yeah. All right, so we definitely have quite a few questions. So the first questions are from Dr. Ryusei. You kind of talked a little bit about the microphone that's on the mission, but can you tell us a bit more about the science that you're doing with the microphone, or recap?
Yeah, so there's several microphones. There's I don't actually know. There's one on the rover that was part of the landing system, and that's the one that recorded the sound of driving. And that's a little bit more of an engineering instrument to sort of monitor what the system sounds like, how it's working. Use sound to diagnose a lot of engineering things that are happening. The more scientifically oriented, if that's a term, microphone is on Supercam. And like I said, we can record audio while we are using the instrument. So as the laser fires and creates those little sparks of plasma, those have a shock wave and that makes that ticking sound. And so the microphone can record the sound returning, and we know the distance to the target because we have to focus on the target with the laser. And so knowing the distance, knowing the speed of light down to the target, and then the delay in the sound coming back, we can actually calculate the sound speed and the air temperature, the air density very precisely using that data. That audio signal, the tick from the laser actually also does change with the rock hardness. So a harder rock will sound subtly different than a softer rock as the laser sort of very, very, very slightly drills into it. And we have people on our team studying that, figuring out what can that tell you about the rock? Does it tell you whether the physical properties of the rock are changing in those couple 100 microns that we're zapping through on the surface? So those are some of the things that it's able to do. It's sort of an add-on to the main instrument. It's primarily a spectroscopy instrument, but it's sort of a nice little bit of bonus science. And we can listen without the laser running and get just wind noise, and we can use that to figure out the wind speed as a sort of a secondary support to the actual weather station META, which has actual wind speed sensors, but Supercam can sort of add its own little bit of extra information about the wind.
All right, thank you. The northern hemisphere, where the landing site is mostly void of magnetic field. Can it be an issue for the rover?
We don't really care about magnetic fields one way or the other. So we don't rely on a compass or anything. So that's true. It's the only magnetic fields left on Mars are really sort of preserved in the southern crust. We think that's from long, long ago, 4 billion years ago or so, when the planet actually had a global magnetic field, and that's sort of been frozen into that ancient crust, but elsewhere it's been destroyed. But the rover doesn't really rely on that. It doesn't really do anything with magnetic fields, so it doesn't really affect us.
All right. Then kind of comment question from David Meyer. Being able to basically control this rover from across the solar system and land it like you guys did is amazing. And then the question is there geological value to visiting the crash site of the heat shield to see what deeper layers have been exposed, or is it too contaminated now?
Yeah, so that's a good question. We probably will, I think we'll definitely avoid the crash site of the Sky Crane because that had fuel in it and that contaminates the whole area. Previous missions have visited their heat shield. The MER rovers visited their heat shield. It was mostly an engineering sort of stop on their mission because engineers get to see what their creation looks like when it gets smashed into a planet at however fast it was going. And you can actually learn a lot about how it's constructed and the dynamics of the landing. As a geology tool, it might help you excavate a little bit, but the nice thing about Mars is it's covered in craters, and the craters are an even better way to get a sort of a scoop out of the surface. So there's talk about, if we go a certain direction as we traverse, should we stop at one of these bigger craters like the Hauhotza or the other sort of similarly sized crater along the way, where you get a nice sort of road cut into the rocks and see the stratigraphy in cross section that way. So big craters can do a lot more for that than just our little dinky heat shield crater. But maybe as an engineering thing, but I don't know of any plans right now to visit any of the debris.
I'm gonna ask his next question because it's kind of related. So what kind of contamination do you expect from the rocket exhaust on that crash site?
I'm not an expert in this. I know it's hydrazine fuel, so I think there would be ammonia and some other contaminants. And I think part of it is also just that those parts of the spacecraft were not as clean. They were not as devoid of organic molecules and things as the rover itself, and especially the sampling system. So there might be just that sort of contamination on top of the contamination from fuel. But again, I'm not a real expert in that. I just have heard that there's contamination that we want to avoid. So I'm just repeating the party line. I don't know.
We don't know any better. It's okay. Next question is from Dr. Perlman. So we have a few of our faculty online tonight. So the holy rocks, are these similar to pumice on Earth, or evidence of past evidence of past volcanic activity?
Maybe. They remain a mystery right now. We have taken more pictures of them. We've seen them. We just drove to a location where there's a holy rock, but it looks darker. Those other ones look kind of lighter. But we're still at a pretty primitive level of understanding of what we're sitting on. We're still not sure whether we're looking at something volcanic or sedimentary made of volcanic sand grains. So it's really an open question right now. What are those holes and what do they mean? It's going to require some up close pictures with Watson, with Pixel, with Sherlock, and some more Supercam and Masscam. We short answer is we don't know. The rocks have holes in them. We're trying to figure out what they mean, how that fits into our understanding of the site from orbit. But going from orbit to this tiny piece of the rock, it's a challenge, and so we're still figuring it out. But yeah, pumice, ash, vesicular basalt are some things that have been thrown around. There are other non-volcanic ways to get holes in rocks as well. So we'll just have to wait and see. We're not really sure yet.
All right, and then we have a couple of comments. One is tisk tisk, heroes aren't supposed to look at the explosions. I think this is the comment on the
if it helps, that's from the rear has cams, so we weren't facing the explosions. That was just, we have eyes in the back of our head.
And then Chloe made a comment that it'd be so cool to go sledding on the Martian sand dunes.
Most of the dunes in this site are not super tall. They're just tall enough to get your rover stuck. They're not the real big ones that you sometimes see.
All right, another question from David Meyer. Since the air is so much thinner on Mars, how does that impact the sound recordings?
So the sounds just sort of sound muffled. I heard someone liken it to being sort of like you're underwater. It's just sort of not as loud. It's harder to make sense of it. But the Supercam sound speed experiment, that's part of what the sound speed tells us, is how dense exactly was the air at the time of the laser shot. And is it fluctuating between shots? Is meaning is there wind blowing? Is there turbulence? All those things we can sort of back out of the sound speed measurement. But in terms of what it actually sounds like, it just kind of makes things quieter and a little bit sort of muffled sounding.
Okay. This next question is from Chloe. Of all the new science we're going to get from Perseverance, what do you think is the most exciting?
I think it's really exciting to, we have a mission with the tools, and we're at a site with the geology to start really doing the astrobiology question. As I alluded to earlier, the other missions have sort of dodged the question a little bit. It's like, we found water, we found habitability, but this mission is explicitly saying we are looking for evidence of life. So we have instruments like Sherlock and Supercam that can find organic molecules, and then of course we're collecting the samples to return to Earth. And so I think the potential of getting a really detailed study of these lake sediments, these delta sediments, and then to bring them back to Earth and study them with, techniques in the lab that haven't even been invented yet. I think that's really exciting. That's sort of the future of the Mars program is, this is the beginning of sort of the next stage where we've learned a lot by going to Mars, but the next step, sort of taking it to the next level, is to bring pieces of Mars back and be able to look at them in the lab. And so that should be super exciting. It's going to be a little while before we get them back to Earth, but when we do, it should be really cool. It should help answer some of those questions that are hard to answer with a rover.
All right. We have another question from David. Is Percy powered by an RTG? And how long do we expect its power to last?
It is. You can see it in this picture. It's this big, it's a cylinder with these radiating fins. Those are actually heat dissipators. So it's a big lump of plutonium in there. It's not a fission reactor or a fusion reactor. It's just a hot piece of plutonium. And that heat is attached to what's essentially a fancy thermocouple, which generates electricity. And that feeds into the battery. And then on day to day, our activities are run off the battery because we draw energy faster than the RTG produces it. So we recharge the batteries overnight and we use the energy during the day to do our measurements. So the RTG, it lasts for quite a while. The Curiosity rover landed in 2012. Its RTG is doing just fine. It's the exact same technology. And it's going to be several years still before Curiosity sees any real noticeable impact on the energy. Eventually, these things do run down. But, the pro and con is that the pro is you don't have solar panels, so you don't have to worry about a dust storm. You can just keep trucking. But the con is you're just going down. Your energy is just going down no matter what. The laws of physics say so. So eventually, these rovers will start to slow down. You won't be able to do quite as much that day. You'll have to, think a little bit harder before you warm up all the joints to move the arm, things like that. And eventually it will shut down, but it takes a long time and it's a very slow decline. So it's not just going to be one day the rover shuts off. It's going to be more of a slow degradation of capabilities over many years.
So it has some time though, right? So
yeah, we got 10 plus years, I would say.
Good. All right, so I think the last question, does the air density limit the range of noise detection?
Probably, but we're not really detecting noises from very far. The Ellipse laser can create a spark out to about 7 meters. Beyond that, we can't make a spark anyways, so there's nothing to hear. So it would just be wind noise, and that's just the wind interacting with our microphone. So I think we can hear the audio of the spark all the way out, the full range, but we have not tested that. I think Mars was a little over 3 meters.
Okay, I think that's all our questions. We do have some comments thanking you for this wonderful presentation and for sharing all this information with us. I definitely had a lot of fun learning about this. When you're talking about the landing site, it reminded me, you showed all those red zones. I'm like, you guys are playing the floor is lava on Mars.
That's right. And the question is the floor actually lava? We don't know yet.
All right. Well, thank you, Dr. Anderson, and giving you a virtual applause, as I'm sure our audience is as well from home. For those of you that are interested, we will be having our interactive space that's included in the link below. We have some new artwork, and we have a little Easter egg in there for you to see if you can find our little model of Percy within the room. So, all right, everybody, thank you for joining us. We'll be back again next month, and have a good weekend.